talks about vectors as forces. So we're going to get into actual applications of vectors. So when we think of force, we usually think of it being associated with like effort or muscular exertion, right? And this is experienced when objects are moved from one place to another. So examples of force include pulling a toboggan, lifting a book, shooting a basketball, or like pedaling a bicycle. And from these examples, we can see that the force can either be something that pushes on an object or something that pulls an object. Okay. When a large enough force is applied to an object at rest, that object ends up moving. Okay, and when a large enough force is applied to an object in motion, that force will either continuously move in that direction, stop, or maybe change directions of motion. Okay, so force is a vector with both magnitude and direction, and all the vector properties that we've studied apply to forces. Okay, so what is a force? If we wanted to actually take a look at forces, we need to know that it's the product between the mass of an object, and remember, like mass always has to be in kilos, and the acceleration due to gravity. So 9.88 meters per second squared. Okay, so an example of this is if something is 1 kilogram in mass, what happens is we multiply that 1 kilogram times 9.8 meters per second squared, and we get 9.8 meters per second squared. So 1 kilogram mass exerts 9.8 meters per second squared. And force uses the unit of measurement Newton, and we denote that by N. Because of the Earth's gravitational field, which acts downward, we say 1 kilogram mass exerts a force of 9.8 newtons. Okay, and a person of 60 kilograms of mass, well, all we would do is like multiply that 60 times 9.8. And we can see that on Earth's surface, a person of 60 kilogram mass exerts 588 newtons. Okay, resultant and composition of forces. So the issue in real life situations is that most of the time there's not just one force acting upon an object, there's going to be multiple forces acting upon an object, okay? So like just for example, think of gravity pulling us down. So the resultant of the several forces is the single vector, is the single force that can be used to represent the combined effect of all the forces. Okay, the individual forces that make up the resultant are referred to as the components of the resultant. Okay, and we've seen this before. We've seen one force, two force, or one vector, two vectors, and then we have like the resultant vector. Okay, and again, it can be more than just two forces. Now, the equilibrium of several forces. So the equilibrium of a number of forces is a single force that opposes the resultant. Okay, so if in this diagram we see that the resultant is moving in this direction, what the equilibrium force is going to do is it is going to basically offset that resultant. It's going to be the same magnitude but opposite direction of the resultant, because what it's going to do is it's going to ensure that the object doesn't move. Okay, so in real life this is actually important because it's important to stop the movement of an object. So here's just a little example. Okay, two children, let's call them James and Fred, are pushing on a rock. James pushes with a force of 80 newtons in an easterly direction. Okay, so we've got never eat shredded wheat. James pushes 80 newtons, okay, easterly, and Fred pushes with a force of 60 newtons in the same direction. So 60 newtons. Okay, determine the resultant and the equilibrium of these two forces. Well, the resultant, we know, is from tip to head, or tail to head, of the two forces added together. So the resultant, let's call it resultant vector, equals 140 newtons, and that's moving east. Okay, therefore, the equilibrium vector is going to be opposite that. It's going to be 140 newtons, and it's going to go in the west direction.